Hello everyone, I'm Tashi Garg. I am from Juniper Networks, and today we are going to address a very serious problem in the cloud infrastructure management, the hidden limitation of static dashboards. Dashboards are supposed to be our eyes into the system, but in reality, so many operate on a delay. That delay create blind spots, and those blind spots can cost uptime, revenue, trust, a lot of issues. So, in this talk, I'll explain why this happens, how Rust help us eliminate those blind spots with predictable low latency monitoring, and what happens when the organization make that shift. So let's see the agenda for the day. We will start by looking at the operational impact of the static dashboard. Then I'll explain why Rust, with its concurrency model determinism, is ideal for real time telemetry processing. We'll also explore some real world results, including a large scale case, and we'll end with a phase roadmap for the adoption. So let's begin with the hidden cost of using static dashboard. So most static dashboard they rely on polling. For example, collecting data at the fixed interval. It could be 30 seconds, it could be 1 minute. It depends on the widget that we are using, the dashboards that's being deployed. So now that means that event can happen well before they appear on the. So that is called the data stillness. So we have measured that across environments, 67% of the network operator reports detection delays, averaging almost 8.5 minutes from the incident onset to the first visibility to the network operator. And because most dashboards they use binary or threshold based health checks, 73% of the anomalies like intermittent packet loss, degraded latencies, they are never flagged at all. So when we combine staleness with these missed anomalies, we end up in a very dangerous blind spots. So for that, we this, they come this reactive monitoring trap. So what happens when these blind spots occurs? They forces teams into the reactive posture. So reactive posture is when you are react after the incident occurs. So they respond only when the issue is already impacting customers. Statistically, reactive monitoring correlates with 2.8 times more service disruptions and 7.4 hours of unplanned downtime per month in the production system. In contrast to this, the event driven real time dashboards, the kind that we are talking today, cut that downtime to 2.1 hours by detecting issues as they happen. To get there, though, we need a system that can process massive telemetry volumes in real time with consistent low latency. And that's where Rust fits in. So, how Rust changes everything. So, when we look at the platform for real time monitoring, two things are non negotiable. One is predictable low latency, and second is high reliability under load. And Rust deliver both of them. So if I keep the points, read out the points, it is zero pass abstraction that let us push through high throughput data processing without runtime or memory. Safety without garbage collection means there is no unpredictable GC pauses when there is a telemetry spike. Ownership model and borrow checker that prevents the race conditions in concurrent workloads, compile time guarantees that eliminates entire classes of runtime error like null dereferences. So this combination makes Rust uniquely well suited for latency sensitive workloads like continuous monitoring. Now, the Rust ecosystem, although the language is very powerful, but the ecosystem is what it makes it completely production ready. To get it to the production stage, we need maybe Tokyo for asynchronous runtime optimized for millions of concurrent IO bound tasks. That is perfect for the telemetry ingestion. So for zero copy serialization, deserialization for massive JSON or protobufs, or even Avro payloads act as any low latency web framework that can deliver live updates to the dashboards, or Crossbeam that can have safe concurrency primitives for multi-core scaling of these telemetry processing. With this tech, we can process millions of data points per second while keeping latency under control. So let's see how this the transformational result when this kind of ecosystem was deployed. So, in a real world deployment where we are replacing the static dashboards with the Rust powered event driven system, we saw that there is almost 63% reduction in MTTR. So, it was from 52 minutes down to 19 minutes. There were 37% improvement for a critical incident, 44% fewer operator errors thanks to the instant feedback, 31% less downtime year over year. And these aren't the hypothetical improvement. They come directly from the production environment from where where these deployments were done. Going forward, let's take a case study where we have a global financial service provider with an environment with almost 12,000, there are more than 12,000 instances that are running across multiple cloud providers. The problem was faced that almost 11 times average detection time, 9.4 hours of downtime per month. So, after migrating to a Rust based real time monitoring backend, they processed 3.2 million telemetry data points per second with less than 5 milliseconds of pipeline latency. The anomalies were detected 65% faster. The incident detection was reduced from 11 minutes to 47 seconds. And the downtime, it was dropped to almost 2.3 hours per month. So from 11 minutes, 9.54 minutes to 2.3 hours per month. That was a huge difference. So that's the operational differences that these real time make. It's seen in the real. So along with Rust, there are other things that can be done. There are a lot of emerging trends these days. When we have real time telemetry, there can be powerful capabilities that can be added on top of it. It could be AI driven anomaly detection. More ML models can be added on top of it that can catch these deviations that are invisible to the static thresholds. NLP based query interfaces can be added when natural language query interface is provided. It can translate questions in the common language into a structured telemetry searches, and even on the UI, a more graph-based visualization, more interactive map, maybe maps of dependencies that can cut diagnosis or time by over 40%. So these can be added on top of it, but the prerequisite, if we consider, is low latency, reliable telemetry pipeline, which Rust already enables. So let's see how we want to implement this. So a typical Rust power monitoring stack may include agent layer, which is lightweight Rust binaries, maybe less than 15 MBs, less than 2% CPU use, and sending telemetry over gRPCs or WebSockets, streaming pipelines that are async processing of multi-core partitioning, real-time API layer that can deliver updates to the dashboard in less than 50 milliseconds, and then the reactive UI. That's where it is, instead of polling, it is getting events from WebSockets or SSE-based dashboards that can update automatically. So there are three common, now while adopting this stack, there will be three common challenges. One is integrating with the legacy environment. So that can be solved with the Rust FFI or gRPC bridges so that you don't have to replace everything at once. Definitely a skill gap that we can start with one self-contained component to build confidence, and then the data volume. filter and aggregate at the agent before sending data upstream. So these challenges are real, but manageable if it is rolled out in stage. Considering the roadmap, it is always recommended a phased approach. So in phased approach, the first month maybe can be for dedicated for auditing all these blind spot, defining baseline MTTRs and downtime. Then couple of months to deploy agent in staging, validating latencies, throughput, detection accuracy. Post that a quarter maybe in rolling out to production, integrating with the incident response tools. And beyond that, it can be dedicated for all these emerging trends integration, like adding ML anomaly detection, domain specific visualization. So, doing in a phased approach will keep the risk low while proving its value early. The key takeaways is static dashboard they create dangerous visibility gaps due to polling delays and limited anomaly detection, Rust deterministic performance, memory safety, concurrency model make it ideal for building real-time monitoring pipelines. In production, this translates to faster detection, fewer errors, significantly low downtime. So Rust powered dashboards aren't just, I would say, tech upgrade. They are more as an operational shift. They let team move from reacting to predicting, from like firefighting to preventing. So once we experience this detecting incident in under a minute, there won't be any going back. That's all from my side today. Thank you.